Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is nuclear physics, radioactivity and half-life. Nuclear physics, exploring the concepts of radioactivity and half-life. The study of nuclear phenomena has revolutionized our understanding of matter, energy, and the fundamental forces governing the universe. The story of radioactivity begins in the late 19th century with Henry Becquerel, who discovered that certain materials emitted invisible rays that could penetrate matter. This discovery led to extensive research by scientists like Marie and Pierre Curie, who identified new radioactive elements such as polonium and radium. Their work laid the foundation for our understanding of nuclear physics. At the core of radioactivity lies the nucleus, the tiny but powerful center of an atom. While most nuclei are stable, some are unstable due to an imbalance of forces within them. To attain stability, these unstable nuclei undergo a transformation, releasing energy in the form of radiation. This spontaneous process is called radioactive decay. There are different types of radioactive decay, each involving the emission of particles or energy from the nucleus. These emissions can alter the atomic structure, changing one element into another. This natural process occurs in many elements found on Earth, as well as in artificially created radioactive materials. One of the remarkable aspects of radioactivity is that it follows a predictable pattern. Scientists observed that radioactive substances do not decay all at once but instead lose their activity gradually over time. This led to the discovery of a key concept in nuclear physics, half-life. The half-life of a radioactive substance is the time taken for half of the material to decay. This means that after one half-life, only half of the original radioactive atoms remain. After another half-life, only a quarter remains, and so on. No matter how much time passes, some part of the substance always remains, but its activity diminishes significantly. Half-life is an intrinsic property of a radioactive substance. Different elements have different half-lives, ranging from fractions of a second to billions of years. For example, some radioactive isotopes decay rapidly, while others persist for ages, shaping the geological and biological history of our planet. Radioactivity has profound applications across multiple fields. In medicine, it plays a vital role in diagnosing and treating diseases. Radioactive isotopes are used in medical imaging techniques such as PET scans to detect abnormalities in the body. They are also employed in cancer treatment, where targeted radiation destroys harmful cells. In industry and archaeology, radioactivity is used in radiocarbon dating, a technique that determines the age of ancient objects by measuring the remaining radioactive content. This method has helped uncover historical mysteries, dating fossils and artifacts from different periods in history. Alpha decay occurs when a nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons, essentially a helium nucleus. Since alpha particles are relatively heavy, they have low penetration power and can be stopped by a sheet of paper. However, they are highly ionizing, meaning they can easily disrupt atomic structures. Beta decay happens when a neutron in the nucleus transforms into a proton and emits an electron, called a beta particle. This process increases the atomic number of the element, effectively changing it into a different element. Beta particles have higher penetration power than alpha particles and can pass through paper but are stopped by materials like aluminum. Gamma decay involves the emission of high-energy electromagnetic waves known as gamma rays. Unlike alpha and beta particles, gamma rays have no charge or mass. They possess immense penetrating power and can only be blocked by dense materials like lead or thick concrete. One of the fundamental concepts in nuclear physics is half-life. The half-life of a radioactive substance is the time required for half of its radioactive nuclei to decay. This concept helps scientists determine the stability of an element and its potential applications. For example, carbon-14 has a half-life of approximately 5,730 years and is used in radiocarbon dating to determine the age of ancient fossils and artifacts. Another isotope, uranium-238, has a half-life of about 4.5 billion years and is crucial for studying geological formations and Earth's history. In nuclear medicine, half-life plays a vital role. Radioisotopes like technetium-99m, which has a half-life of just 6 hours, are widely used in medical imaging to diagnose various diseases. Since it decays quickly, it minimizes exposure to radiation, making it safe for medical applications. Radioactivity is not just confined to natural elements. Humans have harnessed this phenomenon to develop nuclear reactors for energy production. In nuclear power plants, controlled nuclear fission reactions release enormous amounts of energy, which is converted into electricity. However, handling radioactive materials requires extreme caution due to their potential health hazards. Another significant application is in energy production. Nuclear reactors harness the power of radioactive decay to generate electricity. By controlling nuclear reactions, these reactors produce a vast amount of energy with relatively little fuel, making nuclear power an essential part of the global energy landscape. While radioactivity offers immense benefits, it also poses risks. Exposure to high levels of radiation can be harmful, affecting living cells and leading to health complications. This is why safety measures, shielding, and controlled usage are crucial in handling radioactive materials. The discovery of radioactivity not only reshaped our understanding of matter, but also opened new possibilities for science and technology. From exploring the age of the Earth to advancing medical treatments and energy solutions, radioactivity continues to influence modern life in countless ways. As we conclude this discussion, we realize that nuclear physics is not just about studying atoms, it is about unraveling the secrets of the universe. The principles of radioactivity and half-life extend beyond laboratories, shaping the past, present, and future of scientific progress. Thank you, keep exploring, stay curious, and continue your journey of learning with AskPrep. Best of luck with your NEET preparation, and see you in the next lesson.